This is an introduction to Chapter 18, going from Section 18.1 through 18.4. In Chapter 18, we are looking at work and energy for a rigid body. Back in Chapter 14, we looked at work and energy for a point particle. And back in Chapter 14, we had kinetic energy was 1/2 times mass times velocity squared. Now we have a rigid body which can rotate. This rigid body is rotating with an angular velocity of omega, and the kinetic energy is 1/2 the mass times the velocity of the mass center squared, plus, and this is the translational kinetic energy, plus the rotational kinetic energy, which is 1/2 times the moment of inertia about point G times the angular velocity squared. Because you're squaring the velocity of the mass center and also the angular velocity, the kinetic energy must be positive. This is equation 18.2. It's also equation 18.4 and 18.6, and it appears on your equation sheet as equation 18.6. Instead of looking at point G, if you want to look at point O, which is a fixed point, so you have a fixed axis passing through point O, then you can take equation 18.4 and you can say the velocity of the mass center, because point O is not moving, the velocity of point G is equal to the magnitude of the vector r, which goes from point O to point G, times the angular velocity. So you can replace the Vg here with Rg times omega. And then you can pull out the omega squared and the 1/2. You have the moment of inertia from this term here, and then you have the mass times the Rg squared from this term here. But the moment of inertia plus the mass times Rg squared is just the parallel axis theorem, where your old axis was going through the mass center and your new axis is going through point O. So this just becomes 1/2 times the moment of inertia about O times the angular velocity squared. So instead of using equation 18.6 to find the kinetic energy, we can use equation 18.5, which is not on your equation sheet, but if we can do this for point O, which is not moving, we can also do this for the instantaneous center of zero velocity, because at that instant in time, the instantaneous center of zero velocity has a velocity of 0. So this is equation 18.7. If you do it for point O, you can also do it for the instantaneous center of zero velocity. So on your equation sheet, you just have equation 18.7, but you can say point O is an instantaneous center of zero velocity, and you can use this for point O also. And we're going to look at this equation in problem 1 from chapter 18. And then on the following pages in section 18.2, a lot of these equations we saw before in chapter 14, and they don't change for the rigid body. So we already know how to calculate the work done by a variable force, the work done by a constant force we have seen before. The only thing that's a little bit different here, when you look at the work done by the force of gravity, which I would encourage you, just like we did in chapter 14, rather than using our equation 14.7, where you just have kinetic energy and the work done by all the forces, you can use equation 14.20, where you have the potential energy instead of work done by a conservative force. So if we look at the gravitational potential energy rather than the work done by the force of gravity, you just have the change in position in the vertical direction, and this is the change in position for the mass center. So if you have a rigid body which is rotating, just look at how the height of the mass center is changing when you look at gravitational potential energy. Most of the other equations that are listed on your equation sheet for chapter 18 are the same as what they were in chapter 14. So 14.15 and 18.17 are the same. 14.13 and 18.15, the only difference is that now this is the position in the vertical direction for the mass center. 18.16 is the same as 14.14, 1818, that's the same as 1420, which is your work energy conservation law, where you're using gravitational potential energy and the work done by non-conservative forces. Or if you want to, you can use equation 1814, which is the same as 14.7, where this is the work done by all of the forces, and the work done by all of the forces is equal to the change in kinetic energy. We calculate the work done by the force, a force, the same way. So this is the same as equation 14.1. Then we also have the work done by a couple moment. Okay, so this is new for chapter 18. And this definition of kinetic energy in equation 18.7 is new for chapter 18. And equation 18.15 is a little bit different, but everything else we have seen before. Okay, so now in section 18.3, we look at the work done by the couple moment, which is the integral of the couple moment with respect to theta, integrated from the initial angular position to the final angular position. So what you have to be careful of when you sum up all of the work, that is work done by all of the forces and also work done by all of the couple moments. In section 18.4, they give you the work energy conservation law. Instead of using the work energy conservation law where you do the work done by all of the forces, I would encourage you just to use equation 1818, where you look at the gravitational potential energy and the elastic potential energy rather than calculating the work done by the force of gravity and the work done by the elastic force. And then there's a green box which summarizes everything in these 4 sections. So you should read over these 4 sections and pay particular attention to what is in the green box on page 481. And then we have some problems to solve in section 18.4.